9.2 Estimating a population mean. So first we have to obtain a point estimate, which is simply just a proportion. So favorable outcomes divided by number of trials. Stating properties of a student's t-distribution. A t-score is simply just a z-score, except we use a sample standard deviation to calculate the standard error, as opposed to using the population standard deviation, because to calculate the population standard deviation or population standard error, you need the mean, and we don't have that. That's what we're trying to find with the proportion. Um, Typically, when we find a confidence interval, it's the sample proportion plus or minus the z-score times the standard error, which this is simply just going to be in confidence proportion. But we know that to calculate the standard error, we need the standard deviation slash square root sample size. So we have to calculate the standard deviation, which we use to find the error, which is just going to be sample standard deviation divided by square root n. So normally it's standard deviation over square root n, but standard deviation, as we know, is the summation notation of x minus the actual mean squared over n. But we need the mean here, and we don't have that. So instead, we're going to use the sample standard deviation, which is going to take away a degree of freedom, because that's how standard deviations work. So you can calculate it that way, and the standard error is just going to be the sample standard deviation. So samp dev over square root n, which this is the same for the error formula, but to calculate the standard deviation for a sample, it's always n minus 1, which is Bessel's correction, which has something to do with degrees of freedom, as I made in the previous video. So that's a little bit abstract to understand, but we look at William Gossett, who made t-scores, and simply a z-score, but we use the standard error of the sample deviation, which uses Bessel's correction. So it's the same idea here, except actually for t values, and under t charts, it's always going to be to the right. So we can't calculate the probability before, and the way to do so is going to be a little different, simply because if you look up a standard t-score in a table, it's going to give you the probability to the right of the table, which is an issue because usually we have it on the left. It's not really an issue because if you want to calculate, let's say, this interval right here, all you have to do is find the t-score here, find the probability, which includes this entire interval, and then you subtract this t-score, which takes away all that, leaving just that here. So simply put, if you want to find a certain interval area, which is just going to be p x or y, let's just say, you just find the t-score for x, and then you subtract t-score y. Or sorry, it should be x greater than 0. Sorry, it's a little bit abstract here. P greater than x and less than y, which is going to be that formula right there, which I just made off the top of my head. And here degrees of freedom actually matter because we're not looking at the central limit theorem here. So as we know, if you take a skew distribution like this is actually pretty normal, but let's just skew it a little bit like that. Looks a little skewed right here, or skewed left actually. But if you take the central limit theorem, as you can see, this is not a normal distribution. Central limit theorem says as n is greater than 30, or as n approaches a larger number, you get a more normal distribution, and that's because the outliers cancel out, so you'll get a normal distribution. But here, every distribution depends on the degrees of freedom, and that's because of the central limit theorem again. Not sure why they use degrees of freedom and don't just use the sample size, because why would you have to subtract 1 when you can just not subtract anything at all and calculate the standard deviation that way? But it's a little bit strange, and that's what statisticians use. And simply what they do is, because bigger sample sizes lead tighter intervals because it's going to be all centered or more clustered around the true mean. So the probability distribution might look like this. We have to use the chart that corresponds to the perfect t-score or the sample size. So n is going to have all the samples down here, and t is going to have all the y or all the x axis stuff here. So n calculates the degrees of it's actually degrees of freedom, not n. So you have to find the degrees of freedom, and degrees of freedom is just the sample size minus 1. So if you have a sample size of 40, or a proportion, or total trials of 40, you just subtract 1 to get 39. You find the one that's 39, find the t-score, and then it calculates the probability to the right. So it's a little simple to understand. It's just a z-score. And the reason why we have to find the correct degrees of freedom is because different t-scores or different degrees of freedom lead to different distribution shapes. Tighter distribution shapes with the higher ones, as said in the central limit theorem. So here's how to construct the confidence interval for our population. It's the same exact thing. It's just going to be standard error times the t-score, because t-score accounts for the standard error in the denominator. So if you want to ensure that you can have normal distribution, first check if the root distribution is normal. And this is only if the sample size is small, because the central limit theorem hasn't kicked in yet. So if the central limit theorem, if n is less than 30, then the central limit theorem hasn't kicked in, and therefore you have to use these postulates to determine if your data is applicable to a t-distribution for a point estimate. So sample data comes from simple random sampling, so all the data is random. The sample size is less than 5% of the population, and the data is either normally distributed or has large sample size, which is when the central limit theorem is. Basically, when the n is greater than 30, you can ignore all of this because all the averages are more tightly clustered around the actual mean. And as we know, a confidence interval is just basically, we don't say percent chance that the point estimate or the actual population point estimate or the actual population proportion is within that area or interval. Instead, we assume that if we extrapolate that to many graphs, like that percent of the time, that confidence percent interval of the time, it's going to have the actual population mean within it. A critical t-point is just, as we learned before, a critical point is just a certain t-score that corresponds to a certain percentage under the curve. So when Gossett developed t-distribution, he assumed the sample came from a population that's normally distributed, because I don't think he knew about the central limit theorem yet. You can search him up. His name is William Gossett. But most distributions aren't exactly normal, so we have two options. If the original data is normally distributed, it doesn't matter the sample size, but make sure that your sample is less than 5% of the data. Option 2 relies on using the t-distribution. You can still use it if n is less than 15 if the original data is symmetric. If n is between 15 and 30, you can still use the t-distribution, but it should not have outliers, the original data. If n is greater than 30, just ignore everything. You can use it regardless. Determine the sample size needed to estimate this. So if we rearrange the formula, confidence interval, which will write I int is equal to critical t-point times standard error. So we'll just write crit point times standard error, which you can rewrite as square root n times sample standard deviation. And then we have on the crit point, which is just going to be the difference. Point estimates, which write as pi, divided by the standard error, pretty much. So that's by square root. And if we rearrange and find n, which I'm not going to do algebraically because I don't feel like working that much, the n equals critical point times standard deviation, sample standard deviation actually, because of the normality condition, divided by error squared. But realize that for The problem with this formula is that the critical value requires that we know the sample size to determine the degrees of freedom, because how else are we supposed to calculate the critical point and what probability it responds or corresponds to a certain critical point? So there's an error right there because we need to know the degrees of freedom. If we don't know n, which is the total sample size, we can't find the degrees of freedom, which is just n minus 1. And as we know, the critical point is somewhere where a certain probability or a percentage of the data corresponds to. We can't find that either because all the percentages are different depending on the number of sample size. So we just assume that as n becomes infinity, then it becomes more of a normal distribution. Central limit theorem again. It's the key theory for normal distributions or just any distribution. We can just use the formula error equals critical point times standard error, and we simply solve for n equals critical point times standard deviation divided by error squared, which we can calculate as n approaches infinity pretty much. So pretty much this is now not a critical t point, it's now a critical z point. And all the z points, you don't care about the degrees of freedom because it assumes that the population of the sample is approaching infinity or super large, so the central limit theorem takes over. But you need the degrees of freedom if we're using a small point, a critical t point, because a smaller one corresponds to less probability. So